Hello and welcome back to Let's Code Physics. We are taking another big step with our wave function evolver. We are today going to show how you can extend this code into 2 dimensions, so where you're not just graphing the wave function as a function of x and time, but as a function of x, y, and time. In order to do that, I've had to make a few changes to the code. I went ahead and worked those out off camera, just so that you didn't have to see me, tinker with it. Although I have encountered a problem, so I would love your feedback at the end of the episode with the problem I'm encountering, because the code seems to be working for one case, not really so much for the other case. First, let's talk about how the visuals need to change in this code. So previously, we were using the G-curve utility as part of VPython, which is really useful, is able to graph the wave function, but that only graphs a one-dimensional function. It only graphs one dependent variable versus one independent variable. Well, I guess it can graph multiple dependent variables. They just create different graphs. But the important thing is there's only 2 variables involved, right? There's an x and then there's an output. And when we transform this thing into 2 dimensions, we need to be able to graph x and y as independent variables, and then the psi squared as the dependent variables. That's going to require a 3-dimensional environment, because we've got 2 inputs and 1 output. And so what I've done is I've made my own little 3-dimensional grapher. I will probably be trying to change packages. There's some already existing Python packages that allow you to do these surface plots, which is another name for these 3-dimensional plots. I haven't quite learned how to use those yet. Particularly, I need to find out if it's possible to animate those, but that's some research that I'm going to do over the next couple weeks. But for right now, I've just sort of made my own just to see that my actual computational technique works. It doesn't move terribly quickly because we're going from 1 dimension to 2 dimensions, so that means we've taken all that information in the x direction and we're squaring it, right? So it's not like we're doubling it. It's not like we're having a set of information over here and a set of information over here. It's that you fill out this entire square with information, and so that's going to drastically reduce the computational speed. But what I've done to create the graph is I've gone back to the animation window and I'm creating this list of spheres, and I'm affectionately referring to them as dots because that's sort of what they are. They're dots on a graph. And so they're going to have x and y positions that are given by the finite difference mesh that we're setting up. For right now, I've got those set up to be equally spaced just because there's no real preference of x over y. If I ever wanted to make the boundary rectangular for some reason, I could change that, but typically it's going to be square. So it's got those as its x and y coordinates. Those will stay fixed. The z coordinate will change. It's initialized to 0 just to get the spheres out there. So when you first see the animation run, it's going to look like this flat array of spheres, and then it'll pop up into the shape of the wave function. The wave function modulus squared. Let's see. And so basically it's taking this list. So dot list is the list of items that I'm in, is the list of points that we are graphing. So basically it's going to go through all of the calculation, which we'll go over in a minute. Let's see. I've also commented out all this stuff about the integration and the and the expectation values, just because I'm not interested in calculating those quite yet. But down here you can see we're modifying each dot's z coordinate to be the modulus squared of the wave function. I've created this little psi fact just so that way it'll scale it, because the x and y are in different units than the amplitude of the wave function squared is. So that's just there to keep everything in a reasonable scale. That's all that is. So within each iteration of the loop, within each time iteration, it's going to update the z position to be the imaginary part squared plus the real part squared, so that gives you the modulus squared. Again, that's the same thing as the white curve that we were seeing before, only now it's going to be a surface plot. Since we're now in 2 dimensions, since we're now interested in psi being a function of x and y, we have to change the way we set up the finite difference method. So now the psi current and psi previous and psi next and all of that has to be a function of two indices. It's got to be a function of IY and IX. Next, this is the initial setup. Let's go down to the calculation in the loop. So psi next, psi previous, and psi current. Now, instead of just being along that one-dimensional array of x values, it's now in this two-dimensional array of x values and y values. And it's actually pretty straightforward. Instead of having just the second derivative with respect to x, we now have the second derivative with respect to x plus the second derivative with respect to y. There's no mixing of the terms. There's no cross derivatives of derivative with respect to x and derivative with respect to y. It's just two second derivatives. And so what we do is we just take what we had before. So this is the approximation to the second derivative with respect to x. So you notice x is being incremented forward by 1, x is being incremented backwards by 1, and x is kept there in the middle. And all we have to do is tack on this IY. So basically within each piece of the grid, it's doing that for each point. It's looking to the point to the left and the point to the right, and it's using that to approximate the derivative with respect to x. But now what we have to do is we have to add on the same thing, but then we're changing y instead of x. So this is now the approximation to the derivative with respect to y. So you take I incremented forward 1, I incremented backward 1, or up 1 and down 1, and then I at the current point, and you have to keep Ix the same. So these are partial derivatives now. So you're taking a derivative with one independent variable while leaving the other independent variable the same. I sometimes wonder if maybe we should really be so pedantic about the difference between full derivatives and partial derivatives. I know that there's a reason we have them. When we're talking about, different independent coordinates, you're taking a derivative with respect to x. X is not a function of y, so it's kind of unnecessary. I don't know. That's just a teaching frustration of mine. And then of course the endpoint, this last little part that includes the potential energy. So this is the piece that has the actual physics in it, the actual potential energy. Now potential energy has to be a function of both x and y, and then same thing over here, psi is now a function of both x and y. I have those labels backwards, the ix and the iy, just because it made more sense in my head to set everything up by x's and then increment up and down by y. There's nothing really sacred about that necessarily. So let's see, we talked about the grid setup, we talked about creating the new second derivative. The fancy term for that is the Laplacian, is the multi-dimensional second derivative. So the problem I've been starting with is the infinite square well problem, and that's where the potential energy is 0 inside the area of interest and it's infinity outside the area of interest. So the way I'm enforcing that, because I can't actually put an infinity into the code, it stops talking to me after that. It gets kind of upset. So I'm just setting the potential energy equal to 0. We've got our box set up as from -1 to 1 in both the x direction and the y direction, and so we're just going to keep the endpoints fixed at 0, and that's going to simulate having an infinite potential outside of the well. The eigenstates the stationary states of the infinite square well Hamiltonian are these sine functions. Actually, should that be sine or should that be cosine, since I have this thing starting at... Well, I know it worked. Yeah. Sine will work. Sine will work. That's right. I've already tested it. It works. Yeah. When you make your infinite square well start at 0 and go out to a length, you only have sine eigenstates. When you have it go from negative length over 2 to positive length over 2, then you've got sines or cosines. We'll just worry about sines for right now. So we've got our psi initial here set up to be just sine of pi x times sine of pi y. Those turn out to be eigenstates, or stationary states. Eigenstates are stationary states, but it's more helpful to call them stationary states because the wave function modulus squared, the probability density, doesn't change. That's why we call them stationary states. So if I run this, we'll get out our grid of points here, our dot list, and you can see I get my sines. So I've got a sine squared. Now it's not going down into negative because it's the wave function squared. So you get a sine squared out here, a sine squared out here, a sine squared up here, a sine squared up here. So the middle there is 0, 0. Out here is -1, -1. Up here is 1, 1, etc., etc. And so you get this stationary state. The dots are shifting by a little bit because This is an approximation technique. It's not going to perfectly capture the stationary nature of the states, but it is roughly maintaining its shape, kind of like what we saw before. That white curve would oscillate up and down a little bit, but it wouldn't really change qualitatively. It wouldn't change. So this is any integer times pi times x, which is pretty cool. So for example, I can make this a 2 pi x and run it, and that'll be another stationary state. See, it starts out flat and then it pops it up. Of course, with the sine 2 pi x, my grid is not very well. It has a little bit too large of a step size there, and so it's not capturing quite all the detail. But you can see it's roughly maintaining its stationary nature. Looks kind of like aquarium bubbles, I guess. What I'd love to find out would be if there was a way I could connect these into some kind of surface or something. But for right now, this is pretty cool. So what might be fun would be to try to mix some of those eigenstates together. So let's say we had sine, let's see, that's still going to be a stationary state, 1 and 2 there. So let's try taking this one, putting that back to 1s, and then we'll say copy. And we're going to add 2 stationary states together. If you add 2 stationary states, you don't get a stationary state because it's no longer an eigenstate of the Hamiltonian. Actually, let's try 2 and 1 on that one. So we're only making one change to the second one. Okay, cool. So this thing is not quite as it's got the extra lumps over here, but there's a little bit of interference going on between the sine terms. So this one should not be a stationary state, and I think you can kind of see that these outer antinodes here are getting larger. Let's see if we can rotate it. Unfortunately, the rotation gets a bit slow because this thing is churning along so slowly. I've got my dt set to 10 to the minus 4 here because that's already pushing my epsilon up to an eighth, which is probably about as high as it should be. But you can see it's losing some of the weight in the central peak. It's gaining it in some of the outer peaks there, which is exactly the type of thing we saw in the one-dimensional version, but now we're seeing it happen in 2 dimensions. So we see it happening along the x direction, and we see it happening along the y direction here as well, which is pretty cool. Oh, actually, it's gotten a bit lopsided here. So this thing should be remaining symmetric with respect to x. So that indicates to me there's a little bit of an error in the code, or maybe that I don't have my dt set up all that well. But if I make my dt any smaller, this will be a long video indeed. So yeah, so that's pretty fun. I'm going to be taking a look at some, like I said, I'm going to take a look at some different graphing utilities because one of the reasons that it's taking so long is because it's having to update all of these dots. I mean, how many dots are there? Let's see. I've got my nx set to 50. So there's 50 along the x direction, 50 along the y direction. So that is, oh goodness, 50. That wasn't 2,500 dots, was it? Am I doing that math right? 50 times 50? Let's see here. 50 times 50. Yeah, 2,500. Yeah, so that's quite a lot of points to have to churn through, and it's having to update the visuals, and the visual part always makes it go more slowly. So I'm going to see if there's another utility I can use besides VPython. As much as I love VPython, it doesn't seem to have, I haven't found much on VPython in the way of surface plots. If you've got a surface plotting package that you know of that would be useful in Python, please do send it to me. I'd be glad to give it a try. Another issue that I've run into is what happens when I try to create a Gaussian state. So Gaussians are useful because they have this nice little peak. They're what we envision when we think of an average and a standard deviation, and it's also the lowest stationary state of the harmonic oscillator, which I tried setting up here, but I run into some issues when I use this wave function. So here I've got just some normalization constants out in front, the same thing we had before. I've displaced it along the x direction, but I'm keeping it centered in the y direction. So this is pretty much what we had before, except that now it's this y squared plus x squared business, and the x has been displaced a little bit. Yeah, let me show you what I mean by it not working on the animation here. Okay, so I get the Gaussian. There's a lovely two-dimensional Gaussian. And then I get this little ripple happening over on the left-hand side. And physics-wise, I know that shouldn't be happening because this thing is symmetric across the x and it's symmetric across the y. So if that's happening at the left boundary, it should be happening at the right boundary and at the top and bottom boundaries. So that's telling me that I've got some issue in my code, maybe in my finite element approximation. I'm not sure what. And what's really bugging me is why this is happening to my Gaussian, but not to my sine functions. And you might say, well, maybe it's an issue of it being in the infinite square well. Well, let's take a look at that. Let's replace the infinite square well with, actually, let's do it this way. Let's replace the infinite square well with the harmonic oscillator potential. So this is x squared plus y squared. So this is a paraboloid, I think is the term for the three-dimensional version. You see the same things happening here. And in particular, I don't see any changes happening to these dots at all. So I'm not entirely sure what's happening there. We can rotate it around and see that, there's not, I don't think there's much happening over here. It seems like there's basically some noise that starts over here and then it gets distributed over this way. So I am not sure why that is happening. I'm going to leave this code in the description below. I would love to hear your feedback about what might be going wrong with this displaced Gaussian here. In fact, I'm going to get rid of these just because we're not even going to try the higher level, the higher energy states there. So I would love to hear your feedback about that. Maybe I've mistyped something in the finite difference equation, or maybe I'm simply not using enough points. In which case, I'm going to need to find a faster computing solution because this is not moving very fast. I'd probably just have to record it running overnight and then speed it up for the sake of the video. So anyway, thank you so much for watching. I would appreciate any feedback you can provide, and I will see you next time. Bye-bye.